All right, welcome to another exciting day. You can tell I'm full of excitement today. Advanced level chemistry here at Spain Park. Today is Tuesday, October the 1st. October 1st. Okay? We are well on our way. We're all October 15th is the end of the first 9 weeks. Okay? So today we need to finish up just talking about this whole concept of lower energy, higher entropy, Gibbs free energy, and we're just going to practice that. I have the hard copy of the study guide for you, and there's some things on the study guide I want to make sure we kind of go over today. Tomorrow you'll have time to work on the study guide. Okay? You have time to answer questions about the study guide. Study guide will be turned in before class on Thursday when we have the test. Okay? Now, I am not posting answers to the study guide because then the answers are all in the notes and all in the different things, and then you can talk with one another and figure stuff out and learn. But hopefully between today and tomorrow, many of the things that would be questionable, we will go over. Again, there's no real math on this. This is more of a qualitative unit, so we should be in good shape there. So, Jonathan, with enthusiasm, if you're enjoying these videos, what should they do?
Hit that like and smash that subscribe button.
That's better. There we go. A little over the top there, but that's okay. We'll take it. All right. So yesterday we started talking about the two driving forces. Two driving forces. Everything wants to go to lower energy. And from your notes, lower energy always means more what? Lower energy means more stable. It's more stable. Things in nature want to be in the most stable state. Certain bonds are stronger, more stable than others. Carbon and oxygen love to be in the state of carbon dioxide. That's one of the most stable forms for carbon and oxygen to be. So when they're not, when they're like in paper, in cellulose, the carbon and the oxygen are bonded in different ways, they would much rather rearrange and get to the CO2. So exothermic reactions, a negative delta H, is what nature favors. It tries to get to the lowest possible energy state. But we know that endothermic reactions do occur. We did it in the lab. I did it yesterday, the sodium bicarbonate and the acid. It reacts instantaneously. We don't have to add heat. We don't have to do anything. But it gets cold, so we know it's endothermic. What would be the sign of delta H if it's endothermic? Positive. Okay? Because you're putting energy in to make the reaction occur. Now, there has to be a second driving force then, and that second driving force is entropy. And entropy is a measure of what? The disorder. So which has more disorder? A solid, a liquid, or a gas? Gas. Okay, hopefully you can just envision that and see that. Solids are in a crystal lattice structure, a repeating orderly pattern. And then liquids, that pattern breaks apart, they just start rolling around one another, and then we get to a gas, and they completely separate. But what about changes in entropy? If I look at this, changes in entropy, a solid dissolved into a liquid. What do you think happens to entropy in this case? Increases or decreases? Lucas. Why?
Because it's getting more disordered.
What is getting more disordered?
The molecules and the
Which one? Okay, let me keep going.
the liquid, the molecules in the liquid are getting more dispersed.
Okay, but the solid is in what state? What do we call it again? Is it orderly or not? It's a crystal lattice structure, right? What happens to that structure when it dissolves?
It goes away.
It breaks apart, breaks into the individual parts. So rather than being like this, it ends up being like this, okay? Where it's completely surrounded. So the crystal lattice, I don't know if you can see the blue and the green, the crystal lattice breaks apart to where it's no longer, now they can all move around one another. So there's a lot more chaos, a lot more disorder. But what about gases like CO2? Gases dissolve. So this is going to be a positive delta S. You might want to write this just down in your notes. gases dissolve into a liquid. Is the gas going to become more or less disordered if it dissolves in a liquid? Less disordered, right? Because now it's more confined. And as a gas, it can go anywhere and it's spread out to fill the size of the container. But when you dissolve it like CO2 in water, the fizz and pop, now it's confined. Okay? So what would be the sign here? Negative. Okay? Now, the sign of delta S can be determined by comparing moles of gaseous reactants to moles, and it's gaseous, of gaseous products. If moles of gas increase, delta S is positive. All right, so let's look at a practice of this. Two, 1, 2. Once we start practicing this, I think it's going to make a whole lot more sense to you. 1, 2, 3. 1, 2, 1, 2, 3, 4. This is just a practice for in your notes. All right, so we're not going to use the values from appendix C and all that. We're just going to look at the equation. And all we have to do is compare gaseous reactants to gaseous products. So if I look at A, how many moles total of gas do I have on the left? Well, moles, molecules. That's just, we don't know moles, okay? So I forgot that we don't know moles yet. Okay? Moles is just molecules. Let's just count molecules. Okay? How many molecules on the left do we have that are gases? Not atoms, molecules. I got 1, 2, right? How many do I have on the right? Just 1. Again, I'm looking at the whole, the coefficient, not the subscripts. Okay? So I got 2 molecules here, I got 1 molecule here. So as a result, I'm making fewer molecules of gas. Since I'm using this term and I'm throwing it out by accident, okay? How many's in a dozen? 12, right? So, if I said I had a dozen of these and a dozen of those, I'm gonna make 1 dozen of these. So it would be 2 dozen combined together to make 1 dozen, right? It's in a ratio. 1 combines with 1 to make 1. So 10 will combine with 10, and it'll still only make 10. Because they're making bigger molecules. They're combining together. A mole is just this humongous, it's a chemist's dozen. It's this huge number of molecules, but it's just like a dozen is 12. A mole is this 602 sextillion. It's this huge number, but we're going to learn about that next unit. Okay? But we're just going to talk about molecules. 2 molecules make 1 molecule, so the number of molecules of gas are decreasing. You got more molecules of gas here than you do here. So they're going into bigger molecules. You have less chaos because you're decreasing the number of molecules of gas. Okay? So what do you think is the sign of delta S? Are we making more or less chaos? Less. So what's the sign going to be? Negative. Remember, entropy measures disorder. It's becoming more ordered. We're going from 2 molecules of gas just floating around to 1 molecule of gas. So the molecule's bigger, but there's only 1 of them now versus 2. So that means there's less disorder because we only have 1 thing floating around now versus 2. What about here? How many molecules of gas do I have here? 1. How many molecules of gas do I have here? 2. So what's happening to the number of molecules of gas? It's going up. So what's the sign of delta S going to be? Positive. Okay? So here, how many molecules of gas do I have on the left? Gas. Well, what's that little symbol right there? S. Is that a gas? So how many molecules of gas do I have on the left? 0. Do I see a G anywhere over here? Don't make this hard. Do I see a G anywhere on the left-hand side? So do I have any gas as a reactant? No. 0. How many molecules of gas do I have on the right? 1. So do I make more or less molecules of gas? So what is my sign of delta S? Positive. You just look at gas. Okay? So I come down here to this one. That's the one I just did. Come down to this one. How many molecules of gas do I have on the left, on the reactants?
3.
No, I got 5. I got 2 plus 3 is 5. Get your calculators out if you need to. Okay? 2 here and 3 there. I have 5. How many do I have on the right-hand side? 6. So did my molecules of gas increase or decrease? Increase. So what's my sign of delta S? Positive. Okay? So take a second now and you do 54. How many would bet me a nickel you got these 4 right? Okay? So we're kind of just still mixed. Again, we're just counting molecules of gas. So how many molecules of gas do I have on the left? 2. How many do I have on the right? 0. Okay? So are the molecules of gas increasing or decreasing? Decreasing. So what's my sign? Negative. Negative delta S. Okay? Because there's a solid is more ordered than a gas is. So we just look at gas. So how many molecules of gas do I have on the left here? As for the reactants? 0, and I'm producing 3. Okay? 3. So what's happening to my entropy? Positive or negative? Positive. It's going up. More gas means more chaos, more particles, more randomness. Okay? And then on C, how many? Okay, so they just give you a solid calcite, give you the name of that. Okay, but I got 2 molecules of gas versus just 1 molecule of gas, right? So what's happening to delta S? It's negative, right? Okay? And then lastly here, 3 moles of gas going to 6. So what's the sign? It's positive. Okay? So to determine the sign of delta S in a reaction, you just look at the molecules of gas. If you're making more gas, then the sign is positive. If there's fewer, now what if it was 2 and 2? What's the sign? What's delta S going to be approximately?
Delta S.
If it's 2 makes 2 moles of gas, 2 molecules of gas make 2 molecules of gas. Where's the middle of positive and negative?
0.
0. It's going to be near 0. Okay, there's not going to be much change in entropy at all if you have the same amount of gas. Okay, so are we all comfortable with that? Okay, so entropy is the measure of the disorder. We can determine the sign of the entropy by just looking at the molecules of gas that are in reactants compared to products. If the molecules of products is more, then it's going to be a positive. If it's less, it's a negative. All right, so now we just want to apply this to our delta G. Okay, so now let's look at the second part that's on this sheet, right here. This is what we were talking about at the very end of class yesterday. And I left it up over here. It's the Gibbs free energy. This is what ultimately determines whether a reaction occurs or not. These are the 2 driving forces. Sometimes they both say yes, yes, let's make this thing happen. Sometimes they both say no, but other times one is a yes and one is a no. One is a favorable change and one is unfavorable. What's going to determine that? So when we look now at this 65 right here, we have this equation, delta G is equal to delta H minus T delta S. So in 65A, delta H is what sign? And we're not plugging numbers in, we're just really worried about the sign. Because we can figure this out mathematically, it's just in our head, theoretically, right? So delta H is what sign? On 65A, what's the sign of delta H? Negative. So if this is a negative, what's my sign of delta S? Negative. Okay? Negative. Now, is this negative delta H, is that a favorable change? Yes, okay, things want to go, that means it's exothermic, means it's going to a lower energy, a more stable state, so this is a favorable change. But what about a negative delta S? Is that favorable? No, this is unfavorable. So this is a case where mom's saying yes, dad's saying no. Who wins? Generally mom, but it's the favorable versus unfavorable. The only thing that we can change is temperature. So now let's look at this. If we go minus a minus a minus, this is the equivalent of minus and a plus, correct? What's going to determine the sign of delta G?
The sign of temperature.
Whichever term is bigger, right? If this is a 5 and this is a 6, then it's going to be plus 1. If this is a 6 and this is a 5, it's going to be minus 1. Whichever term is bigger is going to determine it. Well, the only thing that we can change is temperature. Which means that if T is small, low temperature, then this whole term is probably going to be small and delta G will probably be negative. But as the temperature gets bigger and bigger and bigger, at some temperature T, this term gets bigger than that term. And in AP chemistry, we actually plug in numbers and we do this, and it's loads of fun, okay? But we're just looking here, at some temperature T, this ends up becoming bigger and the reaction becomes positive and it stops. So this one's a little bit easier. This is only going to be spontaneous at low temperatures. In other words, delta G is negative at low temperatures. Are you following me on that? It's all temperature dependent. It's which sign. Delta G determines whether the reaction occurs. Okay, you just got to trust me on that one. Okay, we're not digging into what delta G really is. It's just this is why some things react and other things don't. Now we can remember it. If they're both negative, it's only going to occur at low temperatures. Negative is low. Negative is at the bottom. So it's spontaneous only at low temperatures. But what if? I'm just going to do a different example. What if they were both positive? Now you're going to have a positive minus a positive. Same thing, right? But now if this term is bigger, what does that mean? Delta G will be negative. So when is it going to be spontaneous? At high temperatures. Now, here's just a very simple example of this one. I don't have a simple example of this one, but a simple example of this one. Ice melting. Okay? When we have ice, it is in a crystalline, orderly structure. Okay? Something nasty on this. So ice looks like this. Okay? It's ordered. But when you melt it, it becomes more disordered. Is that an increase or decrease in entropy? An increase. Positive delta S. Is that favorable or unfavorable? Positive delta S. Favorable. Positive delta S. Reactions tend to go to a higher entropy. Positive delta S is favorable. Okay, we need to know these two things. Okay? Positive, so an increase. So when those bonds, when it goes and turns into water, nature's saying, yes, I'm more disordered, I'm more chaotic. But it takes energy to break those bonds. Melting is an endothermic process. Okay? So when does ice melt? What temperature? 0 degrees Celsius or 273 K. Well, below 273 K, this term, okay, is bigger than this term. So ice doesn't melt. It's a non-spontaneous reaction at low temperatures because this term is bigger than that term. But once you get above 273, now this term gets bigger than that term because temperature is getting bigger, higher and higher and higher and higher. Finally, delta G becomes negative and the ice will melt spontaneously just sitting out on the table. When you're right at 273, it can go either way. It's in equilibrium. It can either freeze or it can melt. It's back and forth. So we can actually mathematically calculate the melting point of ice using this equation, which we do in AP chemistry. That's a big selling point for you now. That man, that's power. That's incredible. Okay. So there's some reactions that are temperature dependent. It's always going to be temperature dependent. It's easy to recognize when both signs are the same. If both signs are the same, it's temperature dependent. Secondly, if they're both negative, it's spontaneous at low temperatures. If they're both positive, it's spontaneous at high temperatures. That helps you memorize and remember it better. Okay? So, knowing all of that, let's look at B. Okay? So we have the sign of delta H. Now there's no sign, so what's the sign assumed to be? Positive. So delta H is positive. Delta H is positive. What's the sign of delta S? It's negative. Okay? Is a positive delta H a favorable change? No. So this is unfavorable. Is a negative delta S a favorable change? No. No. So that's unfavorable. So is there anything driving this reaction just from a theoretical point of view? No. So will this reaction ever occur? No. But now let's look at it mathematically. A positive minus a minus. What's the only possible sign for delta G? Positive. So it's not gonna happen, ever. Doesn't matter what the temperature is. Something has to drive the reaction. Something has to make it want to happen. If you're in a group of friends and nobody wants to go do something, nobody wants to go bowling, you're not gonna go bowling. Okay? Which is crazy to me because it's the best sport. Okay? But, okay? So this is gonna be non-spontaneous at all temperatures, which is, which letter up there? Spontaneous at all, this is gonna be at 2. Okay? This one, negative, negative, again, when's it gonna be spontaneous? Low temperature, spontaneous at high, but not that this is gonna be spontaneous at low, so this would be a 3. Based upon these right up here. Okay? What about this, let's see. Just take 30 seconds, see what you would say. Which one is it gonna be? Just let everybody think about it. Okay, Emily, what do you think?
Or it's not spontaneous at high.
It's spontaneous at high temperatures. They're both positive, right? So now again, you can figure this out mathematically in terms of T is the only thing you can change. But it's simple. If they're both positive, that means it's going to be temperature dependent and it's only going to be spontaneous at high temperatures. Okay? So we can just use this to kind of predict. We can use the equation to predict the sign. So let's just go ahead. Well, I'm going to give you the study guide. And then you can either do those last 2 on this sheet right here. Same principle. Forget what the directions say. Just kind of use the same directions from above on those 2. But just kind of determine, that's all I want you to be able to do, is favorable and unfavorable. Okay, I am going to collect this, but I will always say this, I always make study guides an optional, this will be an optional 20-point grade. So if you are a lazy person and don't want to do study guides, or you feel like you don't need to do it, well then, you don't have to do it. Is that true? But it's going to be a 20-point grade, but if you don't do it, it'll just be a nothing out of nothing. I'm just saying, here's 2 more that you can just practice. Okay? But I'm on the study guide. If you go to the last page, number 20. Well, actually, before I even go to that one, let's come back to this. Let's answer the question here so you have an idea. All right. So, just terminology. We've already kind of answered this question, but I just want to get terminology here. Okay? So here, this is a negative delta H and a negative delta S. What did we say? Is a negative delta S, negative delta H favorable or unfavorable? Favorable. This is the favorable one, okay? And this one was the unfavorable. But we said it's going to be spontaneous at low temperature. So which one of these is driving the reaction? Now, delta H is driving the reaction. That's the one. 2 driving forces. They're both not driving this reaction. Only energy or enthalpy is driving this reaction. Okay? This is an energy-driven reaction. When I look at here, this one is positive and this one is negative. What did we say? Neither one, right? So this reaction doesn't occur because there's no driving force. Neither one is driving it, so nothing happens. On this one, we have a positive and we have a positive. So is this a favorable or an unfavorable change? Unfavorable. So is energy driving this reaction? No. But is this favorable or unfavorable? So it's an entropy-driven reaction. In our magnesium solid plus HCl went to magnesium chloride plus H2 gas, okay? Delta H is negative. Negative delta, come on, I can write. Negative delta H. It got hot, okay? We don't know how hot, I don't have a number for it, but we know it got hot. Okay? What about, this is aqueous, and this is a gas. So what do I know about my sign of delta S?
It's positive.
How do you know?
There's none on the first side, there's one on the second side.
One is specifically, what are we looking for?
One gas.
One gas. Okay? That's exactly right. So I know delta S is positive. So is this favorable or unfavorable? Favorable. Is this favorable or unfavorable? So they're both. This is driven by both energy and entropy. Okay? Yeah, so you understand what I'm talking about now when I say that? Okay? Favorable, you just need to remember this. One's negative, one's positive. These are your favorable changes.
The S value is for page 20 about putting.
No, they didn't. No. You're supposed to predict them.
Oh, I didn't read. Sorry.
So, let's just do 20, number one under 20. And as Emmy said, fill in the sign for delta S. So if I look at this, my sign, I have a solid going to two gases and a gas. So what's my sign of delta S going to be? Everybody get good with positive? Because I'm making more molecules of gas. I'm going from solid to 0 gas to 3 gas. So the sign, all you got to do is put in a positive right here. So now I have a positive and a positive. When is this going to be spontaneous? Positive and a positive. High temperatures. They're both positive. It's going to be high temperatures. So which one's driving this reaction? Okay, again, favored, favored. What's the sign of delta H here? Is that favored or unfavored? So is it driving the reaction? No. What's the sign of delta S? Is that favored? Yes. So what's driving the reaction? Entropy only. Okay, this is challenging stuff. So if there's something that you're not seeing, please ask a question, because I guarantee somebody else is. I can't hear. Yes, ma'am. Oh, no, they're not the same. Okay, here, we got to go do foreign language translation. Enthalpy. I did this in some classes. I may not have done it here. Always equals heat or energy. This is, when you take a foreign language como está usted, you gotta translate that in your brain. How are you? Well, this is foreign language chemistry word, enthalpy. Instead of just calling it heat, they call it enthalpy. And I probably have thrown that word out by accident just because I just used that in AP. But anytime you see the word enthalpy, enthal means energy. This is delta H. Okay? So enthalpy means delta H. That might make it even more simple. Enthalpy is a Latin word for energy and heat. Okay? It means delta H. Okay, good question. See, hey, that's the type of stuff right there. Don't just say, I'm supposed to know what that is. Because there's certain things in here that in my brain, it's just, I've been doing it so long that it just is so common to me that I forget. Just like I threw out the word mold today. I forgot, wait, I hadn't taught you what that is yet. Okay, so you guys got to catch me on that. All right, so don't be afraid to say, hey, what is this? All right, so does everybody understand? So anytime you see the word enthalpy, this is your delta H, this is your delta S. Okay, delta H, delta S. All right, so this is going to give you practice. Now I'm not going to do that. I want to take the last few minutes, and I really want to go through some practice on this. Go back to the first page. At the very bottom. We did this in the lab, but I want to make sure that you understand the differences between physical changes and chemical changes. I'm on the very first page at the bottom. Okay, so is a physical change, what happens to the substance in a physical change? Does it change identity at all? No. So when you're going through and looking at something being, whether it's a physical change or a chemical change, in a physical change, it's still the same substance. It may be in a different form. So are phase changes physical or chemical? Okay? So I need a female to tell me, why is it physical? Why, when ice melts, is that just a physical change? Go ahead. The molecules aren't different. It's still water. It's still H2O, right? It didn't change. But when paper burns, it changes. There's evidence of a chemical change, right? There's change in color, change in odor, change in heat, all of those things, and the paper looks way different at the end than it did at the beginning. Okay, so there's a chemical change forms a new substance with new properties. Okay, so just think about this. And why don't you go through and take, just do those. What is it? That's 6 or 8 of them. And then let's just make sure we can talk about those. And then tomorrow you're going to have the whole period to work on this and ask questions. Okay. Matter of fact, I'm just going to go ahead and let you just kind of do those, and then tomorrow is when we'll actually talk about it. That's all I'm asking you. You figure that out. Don't just take time to think about it. Again, what's the definition of a physical change? Okay? So think about, when you put sugar into water, does the sugar change? That's a rhetorical question, not asking for a response. Okay? So we'll look over all this tomorrow, and I'll answer any questions, and we can make sure on anything tomorrow. Just work on it for the last few minutes, and we'll pick up tomorrow, and go Jags.